Picture this, somewhere deep inside the research facility at CERN, on the border between Switzerland and France, there are scientists keeping something alive, not a plant, not an animal, something far stranger. They have, in a tiny magnetic trap no bigger than a coffee thermos, a small collection of atoms. You couldn't see them without specialized equipment. They exist in a state of extraordinary fragility, suspended in a vacuum colder than outer space, isolated from the surrounding world with extreme care, because the moment one of those atoms touches anything, any surface, any stray particle of air, any ordinary matter at all, it vanishes, it annihilates. It converts instantly into a burst of pure energy and disappears. Those atoms are made of antimatter. The facility where this happens is built across 2 countries, straddling the Swiss-French border in the foothills of the Jura Mountains. Above it, the land looks ordinary. Fields, roads, the small towns and farmhouses of the Gex Plain on the French side, the gentle slopes of Canton Geneva on the Swiss side. You could drive past it and not know what was underneath. But underneath the fields, in tunnels and caverns carved from the rock, there are machines of extraordinary complexity and cost. Rings of superconducting magnets, cooled to temperatures colder than deep space. Detectors the size of cathedrals, assembled from millions of individual components by thousands of engineers and scientists from dozens of countries. Computers processing more data per second than almost any other system on Earth. And in a quieter corner of this vast complex, in rooms that are much smaller and much more modest than the cathedral-sized particle detectors, there are the antimatter experiments, traps the size of a thermos, lasers finely tuned to specific frequencies, electronics that can detect individual photons, and in those small, cold, carefully maintained traps, a few thousand atoms of antihydrogen, the simplest antimatter atoms it's possible to build, kept alive by magnetic fields that prevent them from touching anything made of matter. Those atoms are made of antimatter. And the reason the scientists are keeping them alive, the reason they're devoting enormous effort and resources to this delicate preservation, is that antimatter is one of the deepest puzzles in all of physics. It shouldn't really exist. Or rather, we should have exactly as much of it as ordinary matter, and if that were true, neither we nor the universe would be here at all. The fact that you exist, that the Earth exists, that galaxies and stars and everything we've ever observed exists, is, from a certain angle, a sign that something in the early universe went mysteriously, beautifully wrong. Something broke a perfect symmetry. Something gave matter a tiny, decisive edge over antimatter, and we have no idea what it was. That's the antimatter story, and tonight we're going to walk through all of it, not rushing, not skimming the surface, but going slowly through the whole thing. The history of how antimatter was discovered, which is one of the strangest and most beautiful stories in modern physics. The nature of what antimatter actually is, and why every particle has an antiparticle twin. The mystery of why the universe contains almost none of it, when the laws of physics seem to demand equal amounts. The experiments being done right now to try to find the answer, and the strange, almost science fiction ways in which antimatter has already found its way into everyday human life. If you drift off somewhere along the way, that's perfectly fine. That's what this is for. But if you stay with me, I think you'll find that antimatter is one of those topics that seems bizarre and remote when you first hear about it, but turns out to be completely fundamental to the question of why anything exists at all. Let's begin. The story of antimatter starts not in a laboratory, but in a mind. Specifically, in the mind of one of the strangest and most remarkable scientists who ever lived. A man so quiet, so intensely private, so allergic to unnecessary words, that even his closest colleagues sometimes went weeks without hearing him speak more than a sentence or two. His name was Paul Adrien Maurice Dirac, and in 1928, sitting alone in his rooms at St. John's College, Cambridge, he wrote down an equation that accidentally predicted the existence of antimatter before anyone had the slightest reason to suspect it was real. Paul Dirac was born in Bristol, England, in 1902. His father, Charles Dirac, was a Swiss immigrant who had come to England and made a living teaching French at a local school. Charles was, by all accounts, a difficult man. He was strict, cold, demanding. He insisted that his children speak to him only in French at the dinner table, as a kind of compulsory language lesson. If young Paul couldn't express something in French, he didn't say it at all. He stayed silent rather than stumble through imperfect language. Some who knew him later speculated that this childhood training in enforced silence shaped Dirac's legendarily taciturn personality as an adult. Others think he would have been quiet regardless. Either way, the quietness became his defining characteristic. He became famously, almost comically, economical with words. There are stories about him that have become legend in the physics community, stories that capture the extreme literal-mindedness and social detachment that made him so unusual. At a conference in Copenhagen, a colleague asked Dirac if he had enjoyed the play they had just seen together. Dirac thought for a moment and then said, "There was a mistake in the play. At one point, a character says the sun will rise tomorrow, but the sun does not rise. The earth rotates." That was his review of the play. He once read a letter from his sister, informing him that she had a new boyfriend. He wrote back with 2 questions. 1. What is his age? 2. What are his interests? That was his reply. When he accepted the Nobel Prize in 1933, the prize committee asked him to give a public speech, as all laureates do. He agreed. At the banquet, before a room full of dignitaries and scientists, he gave a speech about the importance of mathematics in physics that lasted less than 3 minutes and contained exactly 0 personal anecdotes. He was married once, to Margit Wigner, the sister of his fellow physicist, Eugene Wigner. When he introduced her to colleagues, he would sometimes say, simply, "This is Wigner's sister," not, "This is my wife." Not even her name, just her relationship to someone else. Margit, by all accounts, found him baffling and endearing in equal measure, and managed to love him anyway for the rest of his life. There is a unit of measurement in physics named after him. A quantity of 100 words per hour is sometimes called a Dirac, because a colleague once calculated that Dirac spoke an average of about 100 words per hour at one of the conferences where he was present. Whether or not the exact calculation is accurate, the story captures something true about him. He was an extreme case of economy in human communication. His published papers are the same. They are remarkably concise, stripped of all decoration, containing exactly the mathematics and exactly the words needed to convey the result and nothing else. Reading them is like reading music. Each element is precisely placed. There is nothing extraneous. His relationship with students was also unusual. He held a professorship at Cambridge, the Lucasian Professor of Mathematics, a chair previously held by Newton and later to be held by Hawking. He lectured. His lectures were extremely good, in the sense that they were precisely accurate and methodically constructed. They were less good in the sense that they were also extremely terse and delivered without any of the theatrical warmth that makes lectures come alive. He would write on the board. He would speak the mathematics. He would stop. Students who asked questions were sometimes met with a pause of several seconds, followed by a restatement of something he had already said, delivered at the same pace, as if the questioner had simply failed to hear the first time. Comprehension difficulties were, in Dirac's model of education, primarily a listening problem. And yet, the people who knew him well, who spent time around him over years, often describe a warmth and gentleness that was simply private rather than absent. He was devoted to his wife and stepchildren. He took long walks in the English countryside and seemed genuinely happy doing so. He enjoyed the Florida warmth after he moved to Tallahassee. He was, by the account of those close to him, not a cold man, but a contained one. A man who expressed himself almost entirely through his mathematics, and who had, perhaps, decided early on that the mathematics was a more reliable and less confusing form of communication than words. I tell you all this not as mere gossip, but because Dirac's personality and his physics were strangely continuous. He brought the same absolute commitment to precision, the same intolerance of ambiguity, the same willingness to follow logic wherever it led without flinching, to his scientific work. He was not afraid of conclusions that were strange or uncomfortable. If the mathematics said something, he believed it, even if the physical implication seemed bizarre. And the equation he wrote down in 1928 said something very strange indeed. To understand what Dirac was doing, you need a little bit of context. By the late 1920s, quantum mechanics was the new framework for understanding the behavior of matter at the smallest scales. Schrödinger had his wave equation, which described how quantum systems evolved over time. Heisenberg had his matrix mechanics. Both versions of quantum mechanics worked beautifully for slow-moving particles, particles moving at speeds much slower than the speed of light. But there was a problem. Einstein's special theory of relativity had shown, back in 1905, that the laws of physics look the same for any observer moving at constant velocity, and that the speed of light is the same for everyone. One of the consequences of special relativity is that particles moving at speeds close to the speed of light behave very differently from classical predictions. Their mass effectively increases. Their energy and momentum are related in a different way than the classical equations suggest. Relativity and quantum mechanics were each wildly successful on their own, but they didn't fit together. The Schrödinger equation wasn't compatible with special relativity. It treated time and space in fundamentally different ways, which is exactly what relativity says you shouldn't do. So the problem in 1928 was to write a version of the quantum mechanical wave equation that was compatible with special relativity. That equation would correctly describe the behavior of fast-moving particles, including the electron. Dirac worked on this problem for months. He was looking for an equation that treated space and time on an equal footing, as relativity required, and that reduced to the correct quantum mechanical equation in the slow-moving limit. He tried various approaches. Nothing worked quite right. And then, in what he later described as a moment of sudden illumination, he found what he was looking for. The Dirac equation, as it's now called, is one of the most beautiful equations in physics. It's compact. It has a deep symmetry. It correctly describes the electron, and it immediately produced a result that hadn't been anticipated. It predicted that the electron has a property called spin, with a value of 1/2. Spin is an intrinsic quantum property, like a tiny internal rotation, and it had been discovered experimentally a few years earlier, but no one had derived it theoretically. The Dirac equation produced spin automatically, as a consequence of combining quantum mechanics with special relativity. That alone would have made it one of the great equations of physics. But the Dirac equation produced something else too, something puzzling. When you write down the Dirac equation and solve it for the energy states of an electron, you get two kinds of solutions. One set of solutions corresponds to the electron as we know it. Negative charge, particular mass, particular spin. These are the ordinary electron states. But there's another set of solutions. Solutions with negative energy. States that seem to correspond to an electron with the same mass and spin, but with negative energy. In classical physics, this wouldn't make sense. A particle can't have negative energy, because negative energy would mean the particle was somehow less than nothing. In classical physics, you'd just throw those solutions away as unphysical. But in quantum mechanics, you can't just throw solutions away like that. All the solutions of a valid equation are potentially real. So what do these negative energy solutions mean? Dirac wrestled with this for a while. He came up with an ingenious, if ultimately imperfect, explanation. He proposed what's now called the Dirac sea. He imagined that all the negative energy states in the universe were already filled, completely filled, all the way down to negative infinity. Since the Pauli exclusion principle says two identical fermions can't occupy the same quantum state, if all the negative energy states are already taken, no ordinary electron can fall into one. The filled sea of negative energy states is invisible, the way a completely filled room is invisible if you're standing outside. It's just the vacuum, the baseline. But now imagine that one of those negative energy electrons in the sea gets hit by a photon with enough energy to knock it up to a positive energy state. The knocked up electron becomes an ordinary electron, and the hole it leaves behind in the sea, the empty negative energy state, behaves like a particle, too, a positively charged particle. Because the sea had a negative charge filling that state, the hole, the absence of that negative charge, looks positive. And because the sea had a negative energy in that state, the hole, the absence of that negative energy, looks like it has positive energy. The hole is a real particle. A particle with the same mass as the electron, but with positive charge. Dirac initially thought this hole might be the proton, since the proton was the only known positively charged particle. But Robert Oppenheimer, the American physicist who would later lead the Manhattan Project, pointed out that if the holes were protons, hydrogen atoms would be unstable and would decay extremely fast. That obviously wasn't right. Hydrogen atoms are among the most stable things in the universe. Dirac was forced to conclude that the holes had to be a new particle entirely, a particle with the same mass as the electron but opposite charge. He called it the anti-electron. He published this prediction in 1931. At the time, this seemed like a bold theoretical speculation, with no empirical basis. No one had ever seen an anti-electron. No one had reason to believe such a thing existed. Most physicists were skeptical, not because Dirac was usually wrong, but because predicting a brand new particle on purely theoretical grounds was a very large claim. The confirmation came sooner than anyone expected. In 1932, just 1 year after Dirac's prediction, a young American experimental physicist named Carl Anderson was studying cosmic rays at the California Institute of Technology. Anderson is worth knowing a little about, because he's one of the great experimenters of the 20th century, and his personal story is interesting. Carl David Anderson was born in New York City in 1905, the son of Swedish immigrants. His father ran a small restaurant. The family was not wealthy, but they valued education. Anderson was an exceptionally able student, and he won a scholarship to Caltech, where he studied physics and engineering. After completing his undergraduate degree, he stayed at Caltech for graduate school, working under Robert Millikan, the physicist who had measured the charge of the electron and won the Nobel Prize for it in 1923. Millikan was fascinated by cosmic rays. Cosmic rays are high-energy particles that stream in from space, originally from supernovae and other extreme astrophysical events, and when they hit Earth's atmosphere, they produce showers of secondary particles. In the 1920s, there was a debate about whether cosmic rays were particles or some kind of very high-energy photons. Millikan himself thought they were photons. He called them the birth cries of atoms. He was wrong. Anderson's experiments would help show that. Anderson built an extraordinarily precise cloud chamber. A cloud chamber works on the principle that a charged particle moving through a supersaturated vapor leaves a trail of ionization behind it, and the vapor condenses along that trail to form tiny droplets, making the path visible, like the contrail left by a jet airplane, but at the scale of individual particles. By surrounding the cloud chamber with a strong magnetic field, Anderson could make the paths of charged particles curve. Positive charges curved one way, negative charges the other. By measuring the degree of curvature, you could determine the momentum of the particle. Anderson set up his cloud chamber and started photographing cosmic ray events. He collected thousands of photographs over the course of several years. Most of them showed familiar particles, electrons and protons, curving in the expected directions. But some of the photographs showed something strange. A track that curved in the direction you'd expect for a positively charged particle, but with a curvature that corresponded to the mass of an electron, not a proton. The track was too light to be a proton, and it was curving the wrong way for an electron. Anderson was careful. He redesigned his apparatus to include a lead plate across the middle of the cloud chamber. If a particle was moving upward, it would lose energy in the lead plate and curve more sharply on the upper half of the track, telling you the direction of travel and confirming the particle's charge. He kept collecting photographs. In August of 1932, he got a beautiful, unambiguous photograph. A particle entered the cloud chamber from below, passed through the lead plate, and continued above. The curvature told him it was positively charged. The track thickness and curvature told him it had the same mass as an electron. There was no other interpretation. It was Dirac's anti-electron. Anderson called it the positron, short for positive electron. It was the first antimatter particle ever directly observed. He published his result in September of 1932. The paper is short and careful. He described the track, gave the measurements, and concluded that the particle had the same mass as an electron but positive charge. He didn't know about Dirac's prediction at the time. He came to the positron purely through experimental observation. When he learned about the Dirac equation and its prediction afterward, he was impressed and relieved. The theoretical prediction confirmed that what he had found was physically real. Anderson was 30 years old when he made this discovery. He won the Nobel Prize in Physics in 1936 at the age of 31. He remains one of the youngest Nobel laureates in physics. He spent the rest of his career at Caltech, also discovering the muon in 1936, another unexpected particle that famously prompted the physicist Isidore Rabi to ask, "Who ordered that?" He died in 1991 at the age of 85. Dirac had already received his Nobel Prize in 1933, shared with Schrödinger, for his equation. The theoretical prediction and its experimental confirmation came within just a few years of each other, which is unusually fast in the history of physics. Usually, theory and experiment are separated by decades. Anderson's positron discovery was the first confirmation that antimatter was real, not just a mathematical curiosity, and it raised an immediate question, one that physicists are still working to answer nearly a century later. If there are anti-electrons, are there antiprotons, antineutrons? Is there an anti-version of every particle in existence? And if there is, where is all the antimatter? Why don't we see it? Why is our universe made almost entirely of ordinary matter? Let me answer the first question, and then we'll come to the much harder second one. Yes, there is an antiparticle for every particle. This is one of the most general and profound results in all of particle physics. It follows not just from the Dirac equation specifically, but from a much broader framework called quantum field theory, which was developed over several decades starting in the late 1920s. In quantum field theory, particles are understood as excitations of underlying quantum fields that fill all of space. The electron, for example, is an excitation of the electron field, and quantum field theory has a deep mathematical property that ensures every field has a corresponding antifield, and every particle has a corresponding antiparticle. This isn't a special feature of electrons. It's a feature of the mathematical structure of the theory. The antiproton was detected in 1955 at the Bevatron Accelerator in Berkeley, California. A team led by physicists Owen Chamberlain and Emilio Segre collided protons together at high enough energy that the collision could produce new particle-antiparticle pairs, including proton-antiproton pairs. They identified the antiproton by its behavior in the detector. It had the right mass and the opposite charge to the proton. Chamberlain and Segre won the Nobel Prize for this discovery in 1959. The antineutron was discovered the following year, also at the Bevatron. The antineutron is particularly interesting because it has no charge. A neutron has no electric charge, so an antineutron also has no electric charge. They look electrically the same, but the antineutron has other properties, like magnetic moment and baryon number, that are opposite to the neutron. When an antineutron meets a neutron, they annihilate just as enthusiastically as any other matter-antimatter pair. Since those early discoveries, Physicists have found antiparticles for essentially every particle in the Standard Model of particle physics. The Standard Model is the theory that describes all known elementary particles and their interactions. It includes quarks and leptons, like the electron, the photon, and other force carriers, and the Higgs boson. Every quark has an antiquark. Every lepton has an antilepton. The force carrier particles, the photon, the gluons, and the Z boson, are their own antiparticles. The W boson has an antiparticle partner, the W with opposite charge. Not all antiparticles are dramatically different from their particle counterparts. The positron is the most obvious case where the antiparticle is clearly distinct, with its opposite charge. But for neutral particles like the photon or certain neutral mesons, the antiparticle is either identical to the particle or very nearly so. Before we go further, let me take a moment to walk you through the Standard Model of particle physics, because it's the framework that tells us what all the particles are, and therefore, what all the antiparticles are. You don't need to memorize any of this. Just let it wash over you. But knowing the landscape helps you appreciate the scope of the antimatter mirror. The Standard Model is the theory that describes all known elementary particles and their interactions. It was built up over several decades, from the late 1960s through the 1970s, through the contributions of dozens of physicists. The people most closely associated with its development include Sheldon Glashow, Abdus Salam, and Steven Weinberg, who unified the electromagnetic and weak nuclear forces into a single electroweak theory in the late 1960s, and who shared the Nobel Prize for this work in 1979. Also important was the work of Murray Gell-Mann, who proposed the quark model in 1964, suggesting that protons and neutrons are made of smaller constituents called quarks, and Gerard Hooft, who showed in 1971 that the electroweak theory was mathematically consistent, a result so technically demanding that his supervisor at the time said, if Hooft is right, he deserves a Nobel Prize. The Standard Model divides all elementary particles into two broad families. The first family is the fermions. These are the matter particles, the building blocks of everything physical. Fermions are further divided into quarks and leptons. There are 6 types of quarks, called up, down, charm, strange, top, and bottom. The names are whimsical labels that don't really mean anything. Quarks are never found alone in nature. They're always bound together into composite particles called hadrons. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 1 up quark and 2 down quarks. The quarks are held together by the strong nuclear force, carried by particles called gluons. This confinement of quarks inside hadrons is one of the most characteristic features of quantum chromodynamics, the theory of the strong force. Each of the 6 quarks has an antiparticle partner, the anti-up quark, the anti-down quark, the anti-charm quark, and so on. Antiquarks bind together to form antihadrons. An antiproton is made of 2 anti-up quarks and 1 anti-down quark. An antineutron is made of 1 anti-up quark and 2 anti-down quarks. The whole hadron structure is mirrored in the antihadron structure. Quarks and antiquarks can also combine with each other to form particles called mesons. A meson is a quark-antiquark pair. The pion, which was first proposed by Hideki Yukawa in 1935 as the carrier of the nuclear force, is a meson. So are the kaons that Cronin and Fitch used to discover CP violation in 1964. Mesons are inherently unstable. They decay quickly into other particles. But they played an enormous role in the development of particle physics, and they play a central role in the search for the answer to the antimatter mystery. Then there are leptons. There are also 6 of these, though they pair up differently from quarks. The electron is a lepton. Its heavier cousins, the muon and the tau particle, are also leptons. The muon is about 200 times heavier than the electron. The tau is about 3,500 times heavier. All 3 of these charged leptons have corresponding antiparticles: the positron, which is the anti-electron, the anti-muon, the anti-tau. These are the antileptons with positive charge. And then there are the neutrinos. Each of the 3 charged leptons has a corresponding neutrino partner: the electron neutrino, the muon neutrino, and the tau neutrino. Neutrinos are electrically neutral and interact with ordinary matter only through the weak nuclear force and gravity. They pass through ordinary matter almost entirely unimpeded. Billions of neutrinos from the sun pass through your body every second, right now, without affecting you in any way you can detect. They're essentially ghosts. Each neutrino also has an antineutrino: the electron antineutrino, the muon antineutrino, the tau antineutrino. Whether a neutrino and its antineutrino are truly distinct particles, or whether they're actually the same particle, is one of the unsettled questions in modern neutrino physics. Particles that are their own antiparticles are called Majorana particles, after the Italian physicist Ettore Majorana, who worked out the theory in 1937 before disappearing under mysterious circumstances on a boat voyage from Palermo to Naples. He was 31 years old. His body was never found. Whether he drowned, was murdered, committed suicide, or went into hiding voluntarily has been debated ever since. He was, by all accounts, a physicist of exceptional talent. Fermi considered him one of the greatest physicists of his generation. Whether neutrinos are Majorana particles or not has enormous implications for baryogenesis and for whether leptogenesis can explain the matter-antimatter asymmetry. The second family in the Standard Model is the bosons. These are the force carrier particles. The photon carries the electromagnetic force. The W boson and Z boson carry the weak nuclear force. The gluons, 8 of them, carry the strong nuclear force. And the Higgs boson, discovered at CERN in 2012, is associated with the Higgs field that gives particles their mass. The photon is its own antiparticle. It has no charge and no distinct antimatter partner. The Z boson is also its own antiparticle. The W boson, which comes in 2 versions, W plus and W minus, with opposite charges, are each other's antiparticles. The gluons are their own antiparticles. The Higgs boson is its own antiparticle. These neutral bosons don't have distinct antiparticle partners in the way the electron does. Now, why is any of this relevant to antimatter? Because the full mirror structure of the Standard Model, every quark mirrored by an antiquark, every lepton mirrored by an antilepton, tells us that if we could assemble all the antiparticles corresponding to all the particles in our universe, we'd have an antiverse that was, in every observable way, identical to our own. Antihydrogen atoms would form the same spectral lines as hydrogen. Antistars would burn the same nuclear reactions, just with antiquarks fusing instead of quarks. Antiplanets would form and develop the same chemistry. Anti-people, made of antimatter, would have the same physical laws governing their bodies, the same mathematics, the same experience of time as people made of matter. The only difference, the absolutely critical difference, is that if a person made of matter and a person made of antimatter shook hands, they would both instantly annihilate in a burst of pure energy. The contact would be catastrophic. This is not a subtle distinction. It's the most fundamental possible difference in terms of interaction, and it's why matter and antimatter can't coexist in the same place. The most dramatic demonstration of antimatter's mirror-like relationship to ordinary matter came with the creation of antihydrogen. If matter and antimatter are truly symmetric, then you should be able to build entire atoms out of antimatter. An antihydrogen atom would consist of a single positron orbiting a single antiproton. It would be the antimatter counterpart of the simplest atom in existence. Antihydrogen was first created at CERN in 1995 by a team called PS210. They produced a handful of antihydrogen atoms, but the atoms were moving too fast to be trapped. They flew through the apparatus and annihilated before any measurements could be made. It was a proof of concept, but not a tool for doing science. It took 16 more years before the Alpha experiment at CERN managed to actually trap antihydrogen atoms and hold them long enough to study them. In 2011, they reported that they had held antihydrogen atoms in a magnetic trap for over 15 minutes, long enough to start doing spectroscopy on them, measuring the wavelengths of light they emitted and absorbed. Why does this matter? Because one of the deepest questions in physics is whether antihydrogen behaves exactly like hydrogen. Does it absorb and emit light at exactly the same wavelengths? Does it respond to gravity in exactly the same way? If antimatter and matter are truly symmetric, then an antihydrogen atom should be absolutely identical in its behavior to a hydrogen atom, just with flipped charges. But if there's any tiny asymmetry, any slight difference in how they behave, that could be a clue to why the universe has more matter than antimatter. So far, every measurement of antihydrogen has been consistent with perfect symmetry. The spectral lines of antihydrogen match the spectral lines of hydrogen to the precision of the measurements. Gravity pulls antihydrogen downward, not upward, just as it does regular matter. Within the limits of what we can measure, matter and antimatter behave identically. This brings us to the central mystery, the deepest puzzle in antimatter physics. If matter and antimatter are so symmetric, so perfectly mirrored, then in the early universe, they should have been created in equal amounts. When the Big Bang produced matter, it should have produced exactly as much antimatter. And if that's true, then as the universe cooled and matter and antimatter moved around and collided, every particle should have found its antiparticle partner and annihilated. The universe should have ended up with no matter and no antimatter, just an enormous bath of radiation, nothing, no stars, no galaxies, no planets, no life. But here we are. Something must have happened to break the symmetry. Something in the early universe must have given matter a tiny edge over antimatter. Not a huge edge, just a tiny one. The best estimates from cosmology suggest that for every billion antimatter particles in the early universe, There were about 1,000,000,001 matter particles. The billion matched up and annihilated. The one was left over. And that one in a billion is everything. Every atom in your body, every star in the night sky, the entire observable universe of matter is the leftover residue of that tiny asymmetry. The question of what caused this asymmetry is called the problem of baryogenesis, or the matter-antimatter asymmetry problem, and it's one of the most important unsolved problems in all of physics. In 1967, a Soviet physicist named Andrei Sakharov, who was also one of the fathers of the Soviet hydrogen bomb and later became a celebrated human rights activist and dissident, wrote a short paper in which he identified 3 conditions that would need to be met for the universe to develop a matter-antimatter asymmetry. These conditions are now called the Sakharov conditions, and they've guided the search for an explanation of matter's dominance ever since. Sakharov was a remarkable figure in ways that go well beyond physics. He was born in Moscow in 1921 into an intellectual family. His father was a physics teacher and amateur pianist who had written popular science books. Andrei was educated partly at home, partly at school, and showed a gift for mathematics from very early on. He was the kind of child who reads textbooks for pleasure, who works through problems in his head while others are playing outside. He entered Moscow State University in 1938 to study physics. When Nazi Germany invaded the Soviet Union in 1941, Sakharov was evacuated, along with much of the university, to Central Asia. He continued his studies in exile, graduating in 1942. Because of his obvious gifts, he was assigned to work in defense industries rather than fighting directly. He worked at an artillery factory in Ulyanovsk, all the while continuing to think about physics in whatever spare time he could find. He later described this period as one of intellectual frustration, tempered by the sense that he was contributing to the survival of his country. After the war, he began his graduate studies in earnest, working under the legendary Soviet physicist Igor Tamm, who had won the Nobel Prize and who recognized Sakharov's exceptional abilities. Tamm had a close and lasting influence on Sakharov, not just scientifically, but morally. Tamm was a man who took ethics seriously, who believed that scientists had responsibilities that went beyond their laboratories. In 1948, Sakharov was recruited into the Soviet nuclear weapons program. The Americans had used atomic bombs on Japan in 1945. The Soviet Union was desperate to develop its own nuclear capability. He quickly became one of the central figures in the development of the Soviet hydrogen bomb, proposing key ideas that turned out to be fundamental to the Soviet design. When the first Soviet hydrogen bomb was tested in 1953, it worked, and Sakharov was awarded the Hero of Socialist Labor. He was 32 years old. He was 3 times awarded that highest honor, and had access to privileges most Soviet citizens could only dream of: a dacha in the countryside, special shops, a car with a driver. He lived a comfortable and privileged life, and for a time, he believed in the work, in the sense that he believed the Soviet Union needed a credible nuclear deterrent to prevent war. But the testing of nuclear weapons in the atmosphere was disturbing him. Each atmospheric test scattered radioactive fallout around the world. The fallout exposed millions of people to elevated levels of radiation. Sakharov started calculating how many people would die as a result of each test, how many cancers would develop decades later, how many children would be born with genetic damage. The numbers were not abstract. they were specific. He felt that every person who died from the fallout was his responsibility in some measure. He began to argue internally for a moratorium on nuclear testing. He sent letters to Soviet leaders. He argued with generals and ministers. In 1963, after years of pressure from scientists like Sakharov on both the American and Soviet sides, a partial test ban treaty was signed, prohibiting nuclear tests in the atmosphere, in space, and underwater. Sakharov felt he had contributed to something genuinely important for humanity, but his dissatisfaction with the Soviet system was growing. He saw the ways in which political ideology distorted science. He saw scientists who disagreed with the party line being suppressed. He saw the agricultural disasters that resulted from the bizarre theories of a charlatan named Trofim Lysenko, who had the ear of Stalin and who managed to suppress genuine genetics research in the Soviet Union for decades, contributing to famines that killed millions. He began to feel that a system that couldn't tolerate honest inquiry was a dangerous system. In 1968, he wrote a famous essay calling for intellectual freedom and international cooperation, circulated underground in samizdat. Soviet authorities stripped him of his security clearance. He could no longer work on weapons. He returned to theoretical physics. He became an increasingly prominent human rights advocate. He won the Nobel Peace Prize in 1975. He was not allowed to travel to Oslo to receive it. His wife, Elena Bonner, accepted the prize on his behalf and read his lecture. When he publicly protested the Soviet invasion of Afghanistan in 1980, the authorities exiled him to Gorky, now called Nizhny Novgorod, a closed city where he was placed under essentially house arrest for 7 years. He was cut off from the scientific community, from foreign contacts, from much of ordinary life. He went on hunger strikes multiple times to protest the treatment of his wife and other dissidents. He was force-fed in hospitals. He continued to write physics papers when he could. He was finally allowed to return to Moscow in 1986, when Mikhail Gorbachev decided that keeping Sakharov in exile was a greater embarrassment than letting him be free. He was elected to the new Soviet legislature in 1989. He died of a heart attack in December of that same year, just as the Soviet Union was beginning its final collapse, having lived to see some of the freedom he had spent decades advocating for finally beginning to arrive. He was, by any measure, one of the most extraordinary human beings of the 20th century, a man who helped build the most terrible weapon ever conceived, and who spent the rest of his life trying to reduce the danger it represented and to expand the freedom of the people who lived in its shadow. And in 1967, in a short paper squeezed between his human rights work and his weapons work, he identified the 3 conditions that remain to this day the foundational framework for understanding why matter survived and antimatter didn't. The 3 Sakharov conditions that he identified in that brief 1967 paper are: first, the process must violate what's called baryon number conservation. Baryon number is a quantity assigned to particles, with ordinary matter particles getting a baryon number of +1 and antimatter particles getting -1. Most processes in physics conserve baryon number, but if you start with equal amounts of matter and antimatter, baryon number total is 0, and you need some process that can convert this 0 into a positive number, meaning more matter than antimatter. You need baryon number violation. Second, there must be violations of 2 related symmetries called C symmetry and CP symmetry. Symmetry, or charge conjugation symmetry, is the idea that the laws of physics look the same if you swap all particles for their antiparticles. CP symmetry combines this with parity, the idea that the laws look the same in a mirror image of the world. If C and CP symmetry were perfectly preserved, any process that created more matter than antimatter would be exactly counterbalanced by a corresponding process that created more antimatter than matter. You need these symmetries to be broken, at least slightly, to get a net matter surplus. Third, the process must happen out of thermal equilibrium. If everything is in perfect thermal equilibrium, detailed balance ensures that any forward process is exactly compensated by its reverse. You need some departure from equilibrium for a net asymmetry to develop. These three conditions, baryon number violation, CP violation, and departure from thermal equilibrium, are the signposts physicists have been following ever since. The early universe was certainly out of equilibrium in various ways, as it expanded and cooled rapidly. So the third condition is almost certainly satisfied. The question is whether there's enough baryon number violation and enough CP violation to account for the observed asymmetry. Within the standard model of particle physics, there is some CP violation. It was first discovered in 1964 by James Cronin and Val Fitch, who were studying the decays of particles called kaons, neutral mesons made of a strange quark and an anti-down quark. They found that kaon decays didn't quite respect CP symmetry. Certain decay modes were slightly more common than their mirror images. Cronin and Fitch won the Nobel Prize for this discovery in 1980. CP violation has since been found in several other systems, including the B mesons, which are heavier relatives of the kaons. These discoveries confirmed that CP violation is a real feature of nature, not a measurement artifact. The standard model has a built-in mechanism for CP violation, involving a particular parameter in the theory that describes how the three generations of quarks mix with each other. But here's the problem. The amount of CP violation in the standard model is too small, much too small, by about 10 orders of magnitude. The tiny asymmetry that kaons and B mesons reveal is not nearly enough to explain the billion-to-one advantage that matter had over antimatter in the early universe. Something else must be providing additional CP violation, some physics beyond the standard model that we haven't yet discovered. This is the central challenge of baryogenesis. We need more CP violation than the standard model provides, and we have no confirmed idea where it comes from. The search for additional CP violation has been one of the driving forces behind particle physics experiments for decades. The Belle experiment in Japan and the Babar experiment at SLAC in California were both designed in part to measure CP violation in B meson decays with great precision. They found the CP violation the standard model predicted, but no new sources beyond it. The LHCb experiment at the Large Hadron Collider at CERN is currently making the most precise measurements ever of CP violation in various particle decays, looking for any departure from standard model predictions. So far, no clear deviation has been found. This is one of the most important searches in modern physics. The stakes couldn't be higher. The answer to why the universe contains matter at all may depend on what these experiments find. Meanwhile, other physicists are looking for the answer in a completely different place, in the properties of neutrinos. Neutrinos are ghostly particles that interact extremely weakly with ordinary matter. They come in three types, called flavors: electron neutrinos, muon neutrinos, and tau neutrinos. In the 1990s and 2000s, experiments showed that neutrinos can oscillate between flavors as they travel. An electron neutrino can become a muon neutrino, and then a tau neutrino, and then back again over the course of its journey. This phenomenon is called neutrino oscillation, and it implies that neutrinos have mass, which was a surprise, since the original Standard Model assumed they were massless. The discovery of neutrino oscillation was rewarded with the Nobel Prize in 2015. The fact that neutrinos oscillate opens a fascinating possibility. If neutrinos oscillate differently from antineutrinos, if the pattern of flavor changes is slightly asymmetric between matter and antimatter versions, then there could be a source of CP violation in the neutrino sector that's large enough to explain baryogenesis. This idea is called leptogenesis, and it's one of the leading candidates for explaining the matter-antimatter asymmetry. In leptogenesis, heavy neutrino relatives called right-handed neutrinos, which haven't yet been discovered, existed in the very early universe and decayed in a way that was slightly different for matter and antimatter. This asymmetry in the decays produced a surplus of leptons over antileptons through various processes in the hot, early universe. This lepton asymmetry then got converted into the baryon asymmetry we observe today. The T2K experiment in Japan, which shoots a beam of neutrinos from a particle accelerator in Tokai to a detector called Hyper-Kamiokande in a zinc mine in Kamioka, has found hints that neutrino oscillations are indeed different from antineutrino oscillations. The data suggest CP violation in the neutrino sector, though not yet at the level of statistical significance that would count as a confirmed discovery. More data is being collected. A next-generation experiment called Hyper-Kamiokande is under construction, with a much larger detector that will be able to measure neutrino CP violation with much greater precision. Results from it in the coming decades may finally tell us whether leptogenesis is the answer. So the question of why there's more matter than antimatter is alive and actively being investigated on multiple fronts. Precision measurements of B mesons and kaons at particle colliders, measurements of CP violation in neutrino oscillations, searches for exotic processes like proton decay that would indicate baryon number violation, studies of antihydrogen to look for any tiny differences from hydrogen. It's one of the most exciting and consequential areas of modern experimental physics. But let me step back from the deep physics for a moment and tell you something you might not expect. Antimatter is not just a laboratory curiosity. It has already found its way into everyday human life in at least one very significant application, and that application is medicine. Positron emission tomography, or PET scanning, is one of the most important medical imaging techniques in use today. You've very likely heard of PET scans, and you may even know someone who has had one done. PET scans are used to diagnose cancer, to study brain activity, to investigate heart disease, to monitor the progression of neurological disorders like Alzheimer's. They're done in hospitals around the world, millions of times each year. And they work by detecting antimatter. Here's how. A PET scan begins with a radioactive substance called a radiotracer. The most commonly used radiotracer is a molecule called fluorodeoxyglucose, which is essentially a sugar that the body processes the same way it processes ordinary glucose, because cells use glucose as fuel. The difference is that the fluorine atom in fluorodeoxyglucose is radioactive. It's a particular isotope of fluorine, fluorine-18, that decays by emitting a positron. A positron is the anti-electron, the same antiparticle that Dirac predicted and Anderson discovered. The patient is injected with the radiotracer. The tracer circulates through the body and gets taken up preferentially by cells that are metabolically active, because active cells consume glucose at a higher rate. Cancer cells, for example, are often highly metabolically active, and they accumulate the tracer in higher concentrations than surrounding healthy tissue. Brain cells also use glucose intensely, and the tracer lights up the active regions of the brain. As the radiotracer decays, each decay event releases a positron. The positron travels a tiny distance, less than a millimeter, before it encounters an ordinary electron. Matter meets antimatter. They annihilate. The annihilation produces two gamma-ray photons, flying off in exactly opposite directions, each with exactly the energy of the electron mass times the speed of light squared, according to Einstein's famous equation E equals mc squared. The PET scanner detects these two photons, coming from opposite directions, and uses their simultaneous arrival to calculate the exact location in the body where the annihilation happened. Repeat this for millions of decay events, and you build up a three-dimensional image of where the tracer has accumulated. In other words, the PET scanner is detecting antimatter annihilating with ordinary matter inside a patient's body, and using the light from that annihilation to create a picture of how organs and tissues are functioning. It's one of the most striking examples of fundamental physics finding its way into practical application. Dirac, sitting alone in his room at Cambridge in 1928, writing down an equation that accidentally predicted antimatter, couldn't have imagined that 90 years later, the anti-electrons his equation described would be used to diagnose cancer in hospitals around the world. Paul Dirac himself had a kind of complex relationship with applications of physics. He was a pure theorist. He loved mathematics for its own sake. He once said, in a lecture, that it was more important to have beauty in one's equations than to have them fit experiment. He meant this seriously. He thought that a beautiful equation was more likely to be right than an ugly one, even before it had been confirmed experimentally. And he was right often enough to make this a plausible view. But he was not particularly interested in applications. The practical consequences of his work were, to him, secondary to the mathematical truth. He ended his career at Florida State University in Tallahassee, of all places, having left Cambridge in the 1960s. He had retired from Cambridge and was looking for somewhere to spend his later years. Florida State offered him a position, and he accepted. He spent the last decade of his life in Tallahassee, continuing to work on fundamental physics until the end. He died in 1984, at the age of 82, still working, still thinking, still following the mathematics wherever it led. He has a memorial in Westminster Abbey, near Newton's grave, which seems right. The mathematical physicist who predicted antimatter, who described the electron precisely for the first time, who first unified quantum mechanics with special relativity, belongs in the company of the great. Let me come back to CERN and the experiments happening right now, because the facility we mentioned at the very beginning of tonight's story, where scientists are holding antimatter in a magnetic trap, is doing something truly extraordinary. They're asking the simplest possible questions about antimatter and checking that the answers are symmetric with ordinary matter. The ALPHA experiment, which stands for Antihydrogen Laser Physics Apparatus, is currently one of the most precise antimatter experiments ever conducted. They've been making antihydrogen since 2010, trapping it since 2011, and over the years they've measured its properties with increasing precision. They've measured its spectrum in the ultraviolet, finding it matches hydrogen to high accuracy. They've measured how gravity affects it. They've measured its charge, finding it to be zero within extremely tight limits. They've measured its magnetic moment. In every case, antihydrogen matches hydrogen. The symmetry holds. But the measurements keep getting more precise. The precision has been improving every year, and the hope is that somewhere in that precision, a tiny discrepancy will appear, a tiny violation of the symmetry between matter and antimatter that could point the way to explaining why matter won. Nobody knows if that discrepancy is there. It might be too small to see, even with the most precise instruments imaginable. Or it might show up in the next generation of experiments. There are other antimatter experiments at CERN as well. The BASE experiment is measuring the magnetic moment of antiprotons with extreme precision, comparing it to the magnetic moment of protons. The ATRAP experiment is also working with antihydrogen. The AEGIS experiment is measuring how antihydrogen falls in Earth's gravitational field, looking for any difference from ordinary matter. So far, gravity appears to pull antihydrogen downward, just as you'd expect. There's no sign of antigravity. This last point is worth dwelling on, because antigravity is a concept that comes up in science fiction all the time. Would antimatter be repelled by gravity rather than attracted? Would it fall upward? The equations of general relativity suggest it shouldn't. But general relativity is a classical theory, and at the quantum level, we don't fully understand how gravity interacts with matter. The experimental tests at CERN are genuinely probing questions that theory doesn't decisively answer. And the answer, so far, is that antimatter falls downward. The AEGIS result was confirmed in 2023, with the first direct measurement of antihydrogen falling in Earth's gravitational field. It went down. This is, in a way, reassuring. It means that general relativity's prediction that gravity is geometric and doesn't distinguish between matter and antimatter is holding up. But it also means we've closed off one avenue that might have led to an explanation of the matter-antimatter asymmetry. The search continues. One thing I find particularly beautiful about the antimatter story is how much of it happened by accident. Dirac wasn't trying to predict antimatter. He was trying to write a relativistic equation for the electron. The prediction of antiparticles was a consequence, an implication of the mathematics that he was forced to take seriously. Anderson wasn't looking for antimatter. He was studying cosmic rays for completely different reasons. He noticed the wrong curving track and figured out what it meant. The PET scanner wasn't invented by people thinking about fundamental physics. It was invented by engineers and medical physicists looking for a better way to image the body, who realized that the positrons from radioactive decay could be used as imaging agents. One thing I find particularly beautiful about the antimatter story is how much of it happened by accident. Dirac wasn't trying to predict antimatter. He was trying to write a relativistic equation for the electron. The prediction of antiparticles was a consequence, an implication of the mathematics that he was forced to take seriously. Anderson wasn't looking for antimatter. He was studying cosmic rays for completely different reasons. He noticed the wrong curving track and figured out what it meant. The PET scanner wasn't invented by people thinking about fundamental physics. It was invented by engineers and medical physicists looking for a better way to image the body, who realized that the positrons from radioactive decay could be used as imaging agents. Let me take a moment to tell you about CERN itself, where so much of the modern antimatter work is happening, because its story is remarkable. CERN, which stands for Conseil Européen pour la Recherche Nucléaire, or European Council for Nuclear Research, was founded in 1954, just 9 years after the end of World War II. The founding was a deliberate act of scientific diplomacy. Europe had been devastated by 2 world wars in 30 years. The scientific community had been scattered by persecution and conflict. Many of the best European scientists had emigrated to the United States, never to return. The founders of CERN, including scientific statesmen like Niels Bohr and the Franco-American physicist Pierre Auger, believed that a shared European scientific institution would help rebuild scientific capacity in Europe and, at the same time, promote the kind of international cooperation that might make another war less likely. It was, in retrospect, one of the wisest investments in the history of science. CERN was founded initially by 12 European nations. Today, it has 23 member states and many more associate members. Thousands of scientists from around the world use its facilities. It has produced a remarkable stream of discoveries, including the discovery of the W and Z bosons in 1983, the discovery of the Higgs boson in 2012, and of course the creation and study of antimatter that we've been discussing. But CERN is known for one other thing that touches almost everyone who uses the modern internet. In the late 1980s, a British computer scientist named Tim Berners-Lee was working at CERN, trying to find a better way for scientists at the facility to share documents and information with each other. The particle physics experiments at CERN involved thousands of scientists from dozens of countries, and keeping everyone informed was a logistical nightmare. Berners-Lee proposed a system based on hyperlinks and a network protocol he called HTTP. He built the first web browser and the first web server. He called the system the World Wide Web. The first website in history was the CERN website. The place that studies antimatter also gave us the internet. That's the kind of institution CERN is. The particle accelerators at CERN have grown dramatically over the decades. The current flagship is the Large Hadron Collider, or LHC, a ring 27 kilometers in circumference that sits in a tunnel beneath the Swiss and French countryside, straddling the border between the two countries. It accelerates protons to within a fraction of a percent of the speed of light and smashes them together with energies that briefly recreate conditions similar to those a fraction of a second after the Big Bang. At those energies, matter and energy are interchangeable, in exactly the way Einstein's famous equation E equals mc squared describes, and new particles and antiparticles can pop into existence from the energy of the collision. This brings me to something worth dwelling on a little. Einstein's E equals mc squared is probably the most famous equation in all of science. Most people have seen it. Fewer people fully appreciate what it says. It says that mass and energy are equivalent. They're different forms of the same thing. Mass can be converted to energy, and energy can be converted to mass. And the conversion factor is the speed of light squared, which is an enormous number. A tiny bit of mass corresponds to an enormous amount of energy. In antimatter annihilation, this equation is operating at maximum efficiency. When a particle and its antiparticle meet and annihilate, all of their mass is converted to energy, every bit of it. None is wasted. This is fundamentally different from chemical burning, or nuclear fission, or nuclear fusion. In chemical burning, only a tiny fraction, far less than a billionth, of the mass of the fuel is converted to energy. The rest remains as matter in different chemical forms. In nuclear fission, about 0.1% of the mass is converted to energy. In nuclear fusion, about 0.4%. These fractions seem small, but are enormous compared to chemical reactions, which is why nuclear weapons release so much more energy than conventional ones. But in antimatter annihilation, the conversion is complete, 100%. If you had a gram of matter and a gram of antimatter, and you let them annihilate, you would release the energy equivalent of about 43 kilotons of TNT. The bomb dropped on Hiroshima was about 15 kilotons of TNT. 2 grams of matter-antimatter annihilation would release nearly 3 times that energy, with nothing left over but pure radiation. This is why antimatter appears so often in science fiction as a fuel or a weapon. In Star Trek, starships are powered by matter-antimatter annihilation in their warp cores. The idea is physically sound. Antimatter really is the most energy-dense fuel imaginable. The problem is making and storing it. At CERN, the entire production of antiprotons amounts to a few nanograms per year. At current production rates, it would take billions of years to accumulate even a milligram of antimatter. And keeping it from annihilating requires elaborate magnetic traps and near-perfect vacuum systems that are extraordinarily expensive to maintain. The dream of antimatter fuel is a real dream, grounded in real physics, but it's not going to be realized with any foreseeable technology. There's something I want to add here about E equals mc squared and antimatter that I find particularly beautiful. When a particle and antiparticle annihilate and produce 2 photons, as positron-electron annihilation does, those photons each carry exactly the energy corresponding to the mass of one electron, according to Einstein's equation. The 2 photons fly off in opposite directions, each with exactly 511 kiloelectron-volts of energy. No more, no less. This is fixed by the mass of the electron and by the equation, and it's extraordinarily precise. It's so precise that the detection of these specific photons is exactly what makes PET scanning work. The scanner knows the energy of the photons that antimatter annihilation produces, because Einstein's equation fixes it exactly. The scanner is designed to detect photons of exactly that energy, coming from exactly opposite directions. The precision of the physics is what makes the medical imaging possible. There's a philosophical thread running through all of this that I want to bring out. Antimatter exists because of symmetry. The mathematical structure of quantum field theory demands that for every particle, there's an antiparticle. The laws of physics are, in some deep sense, symmetric. And yet the universe we live in is not symmetric between matter and antimatter. We live in a universe of matter. The antimatter is essentially gone. This tension between the symmetry of the laws and the asymmetry of the world is not unique to matter and antimatter. You find it in other places too. The laws governing a pencil balanced on its point are symmetric. The pencil can fall in any direction, but once it falls in one specific direction, breaking the symmetry. The laws governing an unstable nucleus are symmetric in certain ways, but the decay, when it happens, goes in one specific direction. Symmetry at the level of laws does not require symmetry at the level of outcomes. In physics, this is called spontaneous symmetry breaking. The laws are symmetric, but the state of the system breaks the symmetry. The Higgs mechanism is a famous example. The underlying equations of the electroweak theory are symmetric between the W boson and the photon, but the lowest energy state of the Higgs field breaks this symmetry, giving mass to the W boson but not to the photon. We live in the broken state. We see the asymmetric consequences. The matter-antimatter asymmetry of the universe is, most likely, another case of spontaneous symmetry breaking in the early universe. The laws were symmetric, but in the hot, dense conditions of the Big Bang, with the inflaton field decaying and the universe expanding rapidly, various quantum fields settled into particular states, breaking symmetries as they went. One of those symmetry-breaking events, somehow, gave matter a tiny advantage. The bill came due later, when matter and antimatter annihilated, and the advantage that matter had accumulated was all that was left. We don't know the details. We don't know which symmetry-breaking event it was, or what the mechanism looked like, or whether it happened all at once or in multiple stages. We have Sakharov's three conditions as a guide. We have CP violation in kaon and B meson decays as evidence that the kind of asymmetry we need is real in nature. We have hints from neutrino physics that there might be a crucial CP violation in the lepton sector, but we don't have the answer yet, and that's actually exciting. It means there's still a profound mystery at the heart of why existence is possible. Why matter won? Why you're here? The answer is out there, encoded in the data of experiments running right now, waiting to be decoded. The search for it is one of the most extraordinary adventures in the history of science. People building vast underground detectors to catch the rare signals of proton decay. People shooting beams of neutrinos hundreds of kilometers through solid rock to measure tiny CP violation effects. People trapping single atoms of antihydrogen in magnetic bottles and shining laser light on them to compare their spectral lines to hydrogens. People analyzing billions of particle collision events at the LHC, looking for the tiny statistical deviation that would point to new physics beyond the standard model. All of them asking the same question, in different ways. Why is there something rather than nothing? Why did matter win? What broke the symmetry? It's one of the most fundamental questions a human mind can ask, and it's being asked right now with the most precise instruments ever built. This pattern of accidental discovery, of finding one thing while looking for another, is one of the most consistent patterns in the history of science, and antimatter is one of the best examples. A mathematical equation predicted it before anyone suspected it was real. A cosmic ray experiment confirmed it serendipitously. Medical applications developed it into a technology that saves lives, and fundamental experiments continue to probe it for clues about one of the deepest questions in cosmology. Let me slow down even further and talk about something that connects the antimatter story to the larger cosmos in a way that I think is genuinely fascinating. Because antimatter isn't only found in particle accelerators and PET scanners. It's being detected in space as well. And what astronomers are finding in space is raising some intriguing possibilities about where the remaining antimatter in our universe might actually be. The Pamela satellite, launched in 2006, and the Alpha Magnetic Spectrometer, or AMS-02, installed on the International Space Station in 2011 and still operating today, have been measuring the cosmic ray spectrum with extraordinary precision. They measure the energy and identity of the particles streaming into Earth's vicinity from space, and they've found more positrons and antiprotons in the high-energy cosmic ray flux than simple models of cosmic ray production would predict. This excess of positrons at high energies was one of the most discussed anomalies in astrophysics for over a decade. What was producing all those extra positrons? There were two main candidates. The first was dark matter. Dark matter is the mysterious substance that makes up about 27% of the mass energy of the universe, that holds galaxies together gravitationally, that we've never directly detected in a laboratory. Some theories predict that dark matter particles, if they're a particular type called WIMPs, for weakly interacting massive particles, would annihilate with each other, and the annihilation products would include positrons. If the dark matter in the galaxy is annihilating and producing positrons, we might detect the excess as an elevated positron fraction in cosmic rays. The second candidate was pulsars, highly magnetized, rotating neutron stars that are known to emit powerful streams of electrons and positrons. A sufficient population of pulsars in our galaxy could produce the observed positron excess through purely conventional astrophysics, without any dark matter annihilation. The debate between these two explanations has been going on for years, and it still hasn't been fully resolved. More recent data from AMS-02, which has collected billions of cosmic ray events, have made the dark matter explanation less favored. The energy spectrum of the excess positrons doesn't match the predictions for WIMP annihilation very well. The pulsar explanation fits better, but the search continues, and there's still room for new physics to show up in the data. This connection between antimatter and dark matter is one of the reasons why cosmic ray antimatter measurements are so important. The universe is full of antimatter detectors now, in the form of space missions and ground-based observatories, looking at the sky and measuring whatever antimatter comes our way from the cosmos. Every new measurement is a potential window into physics beyond the standard model. There are also observations from high-energy astronomy that reveal antimatter annihilation happening naturally in our galaxy. The Integral satellite, launched by the European Space Agency in 2002, detected a bright glow of 511 keV photons from the center of our galaxy. 511 keV is exactly the energy of photons produced by positron-electron annihilation. The galactic center is glowing with the light of antimatter, annihilating with matter. The source of all those positrons is still debated. Supernovae, pulsars, black holes, and dark matter have all been proposed. The galactic center is a complex place, with many energetic processes happening simultaneously, and disentangling the contributions of different sources is difficult. But the signal is unmistakable. The center of the Milky Way is a place where antimatter is being created and destroyed in large quantities, producing a steady glow of annihilation radiation that Integral has been mapping for 2 decades. These cosmic observations remind us that the matter-antimatter separation in our universe isn't perfect. Antimatter is being produced and destroyed all the time by natural processes. What's missing is antimatter in bulk. Antimatter organized into stars and galaxies. Antimatter that has been there since the Big Bang. That primordial antimatter is what's missing. And the cosmic gamma-ray background, if you look at it carefully, shows no sign of the annihilation radiation you'd expect if large regions of antimatter and matter were in contact. The universe really is, at the largest scales, almost entirely matter. The antimatter being produced and destroyed now is all secondary, created by energetic processes and quickly destroyed, not a remnant from the beginning. Let me also mention something about the future of antimatter research. Because there are experiments being planned and built right now that represent the next generation of the search, and they're genuinely exciting. In Japan, the Belle II experiment at the Super-KEKB accelerator is currently collecting data on B meson decays with the highest luminosity, meaning the highest collision rate, ever achieved for this kind of experiment. It will ultimately collect about 50 times more data than the original Belle experiment, and it will measure CP violation in B mesons with extraordinary precision. If there's new CP violation beyond the standard model hiding in B meson decays, Belle II has a real chance of finding it. In Europe, the LHCb experiment at CERN is undergoing a major upgrade. The upgraded detector, called LHCb Upgrade 1, started taking data in 2022, and a further upgrade is planned for the 2030s. The goal is to collect enormous samples of many different types of particle decays, measuring CP violation in systems that haven't been studied in detail before. Charm mesons, strange baryons, and beauty baryons all offer windows into potentially new sources of CP violation. In the neutrino sector, the Hyper-Kamiokande experiment in Japan, under construction and expected to start operations in the late 2020s, will be a huge step forward. Its detector is a tank containing 260,000 tons of ultra-pure water, studded with photomultiplier tubes, sitting in a mountain in Gifu Prefecture. It will measure CP violation in neutrino oscillations with a sensitivity far exceeding the current T2K experiment. If the neutrino sector really is where most of the CP violation needed for leptogenesis is hiding, Hyper-Kamiokande is the experiment most likely to find it. And at CERN, the antimatter program continues. New experiments are being added to the antiproton decelerator complex. The G-bar experiment is measuring the free fall of antihydrogen with even greater precision than Aegis. The alpha-G experiment, a new version of alpha, designed specifically to measure gravity's effect on antihydrogen, has recently produced its first results. The precision of all these measurements is improving every year. If antimatter and matter behave differently in any measurable way, these experiments will find it. This is the landscape of antimatter physics in 2026. It's an active, well-funded international field with dozens of experiments on multiple continents, all working toward the same fundamental goal: understanding why we exist, why matter won. What broke the symmetry in those first fractions of a second? And somehow, none of it would have started without a quiet, peculiar man in a room at Cambridge, following the mathematics wherever it led, unwilling to throw away solutions just because they seemed strange, insisting that the universe had to be consistent with his equations, even when that meant predicting something nobody had ever seen. Paul Dirac, who spoke in sentences of minimum necessary length, who introduced his wife as Wigner's sister, who accepted a Nobel Prize with a 3-minute speech, who lived with extraordinary precision, like his equations, and who saw further into the structure of reality, from his armchair, than almost any other human being in history. Let me now slow down even further and ask the question that I think is the most philosophically interesting one in this whole story. Not what is antimatter, or where did it go, but something deeper, something about symmetry. Symmetry is one of the most powerful concepts in all of physics. When physicists talk about symmetry, they mean something specific. They mean that you can perform some transformation on a physical system, and the laws governing it remain unchanged. Rotate the system, reflect it, shift it in time, move it in space. If the laws look the same after the transformation, you have a symmetry. Emmy Noether, a German mathematician working in the early 20th century, proved one of the most beautiful theorems in the history of science in 1915. Noether's theorem says that every continuous symmetry of a physical system corresponds to a conserved quantity. Translational symmetry in space. The fact that the laws of physics are the same here and in the next room and on the other side of the galaxy gives you conservation of momentum. Translational symmetry in time. The fact that the laws of physics are the same today as yesterday as a billion years ago gives you conservation of energy. Rotational symmetry. The fact that the laws are the same regardless of how you orient your experiment gives you conservation of angular momentum. These are not coincidences. They are theorems. Symmetry is the deep reason behind the conservation laws that physicists use every day. Noether herself had a difficult relationship with the physics establishment for reasons that had nothing to do with her work. She was a woman in an era when women were not considered to belong in mathematics. She was Jewish, in Germany, in a time of rising anti-Semitism. She was a socialist, in a period when that was professionally dangerous. Despite being one of the greatest mathematicians of her era, she was consistently blocked from normal academic positions. Einstein himself wrote letters on her behalf, saying she was one of the most significant creative mathematical geniuses thus far produced. She was eventually given a position at the University of Göttingen, but unpaid. She lectured under men's names. She was forced to flee Germany in 1933, when the Nazis came to power, and ended up at Bryn Mawr College in Pennsylvania, where she died in 1935 at the age of 53, having never received the recognition she deserved in her lifetime. Her theorem is now taught in every graduate physics course. It's foundational, and it connects directly to the antimatter story, because CP violation, the asymmetry between matter and antimatter that Sakharov identified as necessary for baryogenesis, is a violation of a particular symmetry. The CP symmetry is the combination of charge conjugation symmetry and parity symmetry. If this symmetry were exact, Noether's theorem would give you a conserved quantity that prevents the universe from developing a matter excess. The fact that CP symmetry is violated is the fact that this conservation law is broken, and it's the breaking of this conservation law that allows matter to win. Noether's theorem is the framework that makes CP violation so important. It's not just a cute experimental result. It's telling you that the symmetry whose breaking allows matter to exist is not quite exact. The universe has a slight preference, a slight tilt toward matter, and that tilt is encoded in the structure of the conservation laws, or rather, in the failure of one particular conservation law. Now, back to the Dirac sea, because I want to come back to it and say something more, because I find it one of the most audacious ideas in the history of theoretical physics. When Dirac proposed that all the negative energy states were already filled, creating an invisible sea of electrons extending to negative infinity in energy, he was proposing something extraordinary. He was saying that the vacuum, empty space, was not actually empty. It was full. It was full of electrons in negative energy states, packed in so densely that their presence was invisible. We experience them as nothing, as the baseline of reality, as the definition of emptiness. But that emptiness is actually a seething ocean of quantum states, fully occupied. This picture, the Dirac sea, was eventually replaced by a more modern and more mathematically satisfying framework, quantum field theory, which describes antiparticles not as holes in a sea, but as independent entities, excitations of antifields. But the Dirac sea idea had a profound philosophical impact. It suggested that what we call the vacuum, what we call nothing, is actually something. It has structure. It has energy. It fluctuates. In modern quantum field theory, the vacuum is indeed not empty. Virtual particle-antiparticle pairs spontaneously appear and disappear in the vacuum all the time. They borrow energy from the uncertainty principle, exist for a brief instant, and then annihilate back into nothing. These virtual particles are not observable directly, but their effects on real particles are measurable. The Casimir effect, in which two uncharged metal plates placed very close together in a vacuum attract each other because of the virtual particles between them, is a direct experimental confirmation that the vacuum is not empty. The plates have been measured pulling toward each other by precisely the force that quantum field theory predicts. The vacuum is active. It fluctuates. It's alive, with virtual pairs of matter and antimatter constantly appearing and disappearing. This means that even in the most empty region of space, matter and antimatter are being constantly produced and destroyed in tiny quantum amounts for tiny fractions of time. The universe is, at the quantum level, full of antimatter all the time, even in apparently empty space. It's just virtual. It's just transient. It appears and vanishes before anything can interact with it in a lasting way. But it's there. Or rather, the quantum field that gives rise to it is there, always ready to produce it, always producing it and destroying it in an endless quantum dance. This picture of the quantum vacuum, active and fluctuating, and full of virtual antimatter, is one of the deepest things that physics has revealed about the nature of reality. The void is not void. Nothing is never nothing. Beneath the stillness of apparently empty space, there's a constant ferment of creation and annihilation at the tiniest scales. You could think of it as the universe refusing to be at rest. Even at absolute zero temperature, even in the complete absence of any particles or fields, the quantum vacuum still fluctuates, still creates and destroys, still hums with a kind of energy that has no classical counterpart, the energy of nothing, which is not actually nothing. That's a strange and beautiful thing to contemplate. as you drift toward sleep. The antimatter that we talk about in particle accelerators and PET scanners and cosmic rays is the real, observable variety. It persists long enough to be detected, to interact, to annihilate with a visible burst of energy. But underneath all of that visible antimatter is the virtual kind, the quantum kind, the kind that fills the vacuum and makes the Casimir effect real, and the Lamb shift measurable, and the whole structure of quantum field theory consistent and true. The universe is, in some sense, made of both matter and antimatter, all the way down. It's just that the real, persistent, large-scale antimatter is almost entirely gone, and the virtual, transient, quantum-scale antimatter is everywhere, all the time, participating in the fabric of reality without ever quite becoming real enough to see directly. That's antimatter. That's the whole story, strange and beautiful and still unresolved at the deepest level. Let me tell you the story one more time, very briefly, so it can settle into your mind like something soft and quiet. In 1928, a quiet man at Cambridge followed the mathematics and predicted a mirror world. In 1932, a young physicist noticed a particle curving the wrong way in a cloud chamber and confirmed the mirror was real. In 1955, the antiproton was found. In 1967, a Soviet physicist who built hydrogen bombs and fought for human rights wrote down 3 conditions that explain why we're here. In 1964, 2 American physicists found a tiny crack in the mirror's perfection, a violation of CP symmetry in kaon decays. In 1995, antihydrogen was first created. In hospitals around the world, positrons are annihilating with electrons inside patients' bodies every day, making tumors visible on screens. In space, the alpha magnetic spectrometer is counting cosmic ray positrons. At CERN, scientists are holding antimatter alive in magnetic traps and shining laser light on it and waiting to see if it reveals any secret. And the question is still open. We don't know why matter won. We don't know what broke the symmetry. We're still looking. You are the consequence of the question still being open. You're here because matter won. You're curious because consciousness followed. And tonight, you've spent some time with the question. That's a genuinely wonderful thing to have done. Let it all drift now. Let the antimatter be wherever it is. Let the symmetry be as broken as it is. Let the physicists keep working. Let the questions stay open for one more night, while you rest. Let me now slow all the way down, and let the story settle. You've been on quite a journey tonight, if you're still with me. We started in a research facility at CERN, with scientists keeping antimatter alive in a magnetic trap. We went back to 1928 and the quiet rooms of Cambridge, where Paul Dirac wrote an equation that changed everything. We followed Carl Anderson to his cloud chamber photographs, where a particle curving the wrong way announced the existence of antimatter to the world. We walked through the Standard Model and its vast menagerie of particles and antiparticles. We learned about Sakharov and his hydrogen bombs, and his human rights activism, and his 3 conditions. We explored the experiments, looking for CP violation in kaons, and B mesons and neutrinos. We visited the PET scanners in hospitals where antimatter annihilation is used to see inside living people. We looked at the positron excess in cosmic rays and the annihilation glow from the center of our galaxy. And through all of it, the same question has been there, underneath everything. Why is there something rather than nothing? Why did matter win? Why are we here? We don't know yet. We have clues. We have Sakharov's roadmap. We have experimental hints from kaon decays and neutrino oscillations. We have facilities around the world collecting data right now. But we don't have the answer. And there's something quietly beautiful about that, when you let it in. The most fundamental question about why you exist is still open. The people working on it are extraordinary human beings doing patient, precise, difficult work. They're not going to give up. The accelerators are running. The traps are holding their antimatter. The data is accumulating. The answer may be close. It may be decades away. We don't know. But the question is being asked. Seriously, rigorously, with the best instruments human civilization has ever built. That matters. That's something. You can let the whole story drift now. You don't have to hold any of it tightly. Let the characters float away. Paul Dirac, silent in his room, following the math. Carl Anderson, patient with his photographs. Andrei Sakharov, writing physics papers while under house arrest, refusing to give up on either physics or freedom. The scientists at CERN tonight, watching their magnetic traps, listening to their detectors, updating their data files. Let it all blur into the general sense that the universe is deeply strange and deeply beautiful, and that there are people in it who have devoted their lives to understanding it, and that you've spent some time tonight touching the edge of what they know and what they're still trying to find out. That's enough. That's more than enough. Your breathing is slower now, I hope. Your body is settling into its place. The night is quiet around you. And out there in the cosmos, far from any planet, in the darkness between the stars, antimatter is wherever it is, doing whatever antimatter does, not touching anything, not annihilating anything, just being itself, in the vast spaces where matter and antimatter no longer meet. And here you are, made of matter, made of the winning side of a cosmic asymmetry that we still don't understand, made of the one particle in a billion that survived, made of the residue of the Big Bang, made of stardust that was made possible by a symmetry-breaking event that happened in the first fraction of a second of the universe's existence, and that physicists have been trying to understand for 60 years. You are the consequence of the universe choosing matter, in some sense. Not you specifically, but the matter you're made of, the quarks in your protons, the electrons in your atoms. They exist because something in the early universe tipped the scales slightly their way, and from that tiny tip, everything follows. Stars and planets and oceans and life and you, lying here, drifting toward sleep, thinking about antimatter. It's a strange and wonderful lineage to have. Think of it as you fall asleep. You are the universe's way of wondering about itself. You are matter that has organized itself into a thing that can ask why matter exists. You are the residue of the Big Bang, billions of years later, curious about the event that created you. That's an extraordinary thing to be. That's one of the most extraordinary things in the known universe. And all of it traces back, in one chain of causation, to a tiny asymmetry in the first fraction of a second, to a symmetry that broke just slightly, to antimatter losing by just 1 part in a billion, to the universe, in its first blind moments, choosing matter. Rest now. Let the antimatter be wherever it is. Let the matter that makes you be what it is. Let the physicists keep working on the question you don't have to answer tonight. Let the data keep accumulating in the laboratories and on the satellites and in the particle detectors while you sleep. The universe is still doing its quiet work. The atoms in your body are still vibrating at the frequencies quantum mechanics prescribes. The electrons are still in their orbitals. The quarks are still bound inside their protons, held by the strong force in its inexplicable but reliable way. Everything is where it should be, including you. Let your thoughts go soft. Let the ideas blur into something simpler and more restful. Let yourself drift down, slowly, into the place where thinking stops and sleep begins. You've done well to travel this far tonight. You've held some difficult and beautiful ideas. You've let yourself be small and curious in the face of something very large and very strange. That's a good way to spend an evening. Sleep well. The antimatter is exactly where it should be. You are exactly where you should be. And the answer to why you exist is being searched for, right now, by people who have given their lives to the question. Rest well. You are here because something chose matter, and that's a good thought to fall asleep to. Sleep well. The universe seems, at its most fundamental level, to be built on symmetry. The equations of physics look the same if you replace a particle with its antiparticle. They look the same if you run time backwards. They look the same if you reflect everything in a mirror. These symmetries, C, T, and P, and their various combinations, are embedded in the mathematics of quantum field theory. They're not accidental features. They're consequences of the deep structure of the theory. And yet the universe we live in violates these symmetries. Not completely, not obviously, but in tiny, subtle ways that physicists have to work hard to detect. The kaon experiments of the 1960s showed that CP symmetry was broken. The T2K experiment suggests CP violation in the neutrino sector. The matter-dominated universe itself is evidence of a broken symmetry. Why does the universe break its own symmetries? Why does it have rules and then not quite follow them? This is one of the deepest questions in physics and philosophy. The standard answer is that the symmetries are approximate, that the underlying laws are symmetric, but the state of the universe breaks the symmetry. Just as a round ball balanced on the tip of a pin has rotational symmetry, but the moment it falls one way, the symmetry is broken. The laws governing the ball are symmetric. The state of the ball is not. This is called spontaneous symmetry breaking, and it's a concept that runs through modern physics in many important ways. The Higgs mechanism, which gives mass to the W and Z bosons, is an example of spontaneous symmetry breaking. The development of magnetic order in a magnet is another. The idea that the matter-antimatter asymmetry of the universe arose from a symmetric initial state through symmetry breaking is attractive and is incorporated in most theories of baryogenesis. But it doesn't fully answer the question. Because you can ask, why did the symmetry break in the direction of matter rather than antimatter? If the laws are symmetric, the symmetry breaking could have gone either way. Some regions of the multiverse, if the multiverse exists, might have broken in the direction of antimatter. Those regions would contain stars and planets and, perhaps, life made of antimatter. They'd be just like us, but everything would be reversed. And if they ever encountered our region, the collision would be catastrophic. A universe of antimatter meeting a universe of matter would produce the most energetic event imaginable. Pure conversion of everything into radiation. This is, of course, highly speculative, but it illustrates something interesting. The matter-antimatter asymmetry of our universe might not be a fundamental feature of physical law. It might be a feature of our particular region of a larger multiverse. The laws might be symmetric. Our corner of reality might have happened to break toward matter. Cosmologists have explored this possibility, imagining universes where pockets of matter and antimatter are separated by vast distances and have never encountered each other. Whether this is true, we don't know. There's something almost poetic about it. The reason we're here, the reason matter won, might be essentially the same kind of reason that a coin lands heads half the time. The coin is symmetric, but each individual flip breaks the symmetry one way or the other. We live in a flip that came up matter, and we're using the matter we're made of to try to understand why the flip went the way it did. That's the antimatter story. From Dirac's quiet room at Cambridge in 1928, to Anderson's cloud chamber photographs in 1932, to Sakharov's three conditions in 1967, to the kaon experiments that found CP violation, to the trapping of antihydrogen at CERN, to the PET scanners in hospitals around the world, to the neutrino experiments looking for the answer in Japan, to the philosophical question of why symmetry broke in our favor, to the possibility that in other parts of the multiverse, stars shine with antimatter light. It's one of the most extraordinary stories in science. It begins with an equation that was too beautiful to be wrong, and ends with questions that are still open. And somewhere in the middle, it touches almost every deep idea in modern physics. Quantum mechanics, special relativity, symmetry and its breaking, the Big Bang, the early universe, the Standard Model, neutrino physics, cosmology, the multiverse. The thread of antimatter runs through all of it. You can let that settle now. You can let the story drift into whatever corner of your mind stores things you find interesting. You don't have to remember all the details. You don't have to hold on to the names or the dates or the specific experiments. The shape of the thing is enough. The fact that there's a mirror world, the fact that we're made of the winner's side, the fact that people are in laboratories right now, tonight, trying to understand why. The scientists at CERN are still working. The detectors are still collecting data. The magnetic traps are still holding their tiny clouds of antihydrogen, keeping them alive in their magnetic bottles, watching to see if they behave differently from hydrogen in any way that might reveal the secret. It's patient, careful, meticulous work. The kind of work that happens in the middle of the night as well as the day, because the experiments run continuously. While you sleep, the data accumulates. There's something restful about that if you let it be. The universe is being investigated right now. The deepest questions are being asked right now, and you don't have to be the one asking them tonight. You can rest. You can let the scientists do their work while you do yours, which is simply to be alive for another night, to breathe in and out, to let your body rest and your mind drift. Think about what we've covered tonight. A quiet, unusual man named Dirac, writing down an equation in 1928 that was too mathematically beautiful not to be right. The equation accidentally saying that every particle has a twin with opposite charge, the twin being confirmed in 1932 by a young physicist who noticed a track curving the wrong way in a cloud chamber, the antiproton being found in 1955, antihydrogen being built in 1995, all of it being held in magnetic traps and examined with exquisite care in CERN labs today. Sakharov, who built hydrogen bombs and then spent years under house arrest fighting for human rights, somehow finding time in 1967 to write down the 3 conditions that explain why the universe has more matter than antimatter. Those conditions becoming a roadmap for generations of physicists who follow the clues in kaon decays and neutrino oscillations and antihydrogen spectra. PET scanners using positrons to map disease and brain activity inside living people. Medicine made possible by pure physics, discovered almost a century ago. The strange thought that our universe might be one of 2, that somewhere out there might be stars made of antihydrogen and anticarbon and antinitrogen, burning with the same kind of nuclear fire as our stars, but made of the opposite of everything we're made of. All from one equation, all from one man's insistence on following the mathematics wherever it led, no matter how strange the destination. Let your thoughts go soft now. Let the details blur. The specifics don't have to stay. The feeling of the story is what matters. The sense that reality has a mirror, that we live on one side of it, that the other side might exist somewhere, that the question of why this side won is one of the most profound and beautiful open questions in all of science. Your breathing is slower now. Your body is settling. The questions are large, and the night is quiet, and you have nowhere to be and nothing to figure out before morning. The antihydrogen is still in its trap. The neutrinos are still oscillating. The LHCb detector is still recording collisions. The data is still coming in, and none of it needs you tonight. All of it will still be there in the morning, this conversation between human minds and the deep structure of the universe, patient and ongoing and extraordinarily beautiful. Let the antimatter be what it is, somewhere out there in the cosmos, in whatever quantities exist, doing whatever antimatter does in regions of the universe we can't see. Let the matter that makes you up be what it is, the survivor, the 1 in a billion, the consequence of a symmetry that broke just slightly in the right direction. You are here because something in the early universe tilted toward matter. You are here because a coin flipped in your favor before you existed to call it. That's a strange and wonderful thing to be. And it's a good thought to fall asleep to. The universe chose, in some sense, for you to be here. Not you specifically, not this particular arrangement of atoms, but the matter you're made of, the kind of matter that makes stars and planets and living things. That matter got the advantage it needed in those first fractions of a second after the Big Bang. And 13.8 billion years later, here you are, drifting toward sleep, made of stardust that survived, made of the winning side of a cosmic asymmetry that we still don't fully understand. Rest well. The night is quiet, and the universe is large, and the antimatter is exactly where it should be. Wherever that is, not here, not touching anything, not annihilating anything, just being whatever antimatter is in the dark between the stars. And you are here, warm and breathing, made of matter, on the right side of the greatest asymmetry in the history of everything. Sleep well.